Okay, and guys, it's time to start now. Any questions? All right. Today we will start a new section, Taylor and Maclaurin series. Maclaurin. Okay. The goal is for a certain function, find the power series repetitions. The goal. Now, if we have a general function, how do we find a power series? Find the power series repetitions. Find power series repetition of a function fx. Okay. Remember, we have Lagrange mean value theorem. The Lagrange mean value theorem. Lagrange mean value theorem says the following. Mean value theorem. Mean value theorem. Says the following. Suppose if f is differentiable, fx is a function that continuous on closed interval a to b, and differentiable on open interval a to b, and it's differentiable on open interval a to b. Then the conclusion, then there exists a number c in a to b such that fb minus fa equals f derivative c b minus a. Okay. Remember, we have linear approximation. This actually uses mean value theorem. We can derive the idea of a linear approximation. Linear approximation says, so fx minus fa equal to f derivative a x, this, x minus a. So the reason is, suppose the function is nice. For instance, second derivative exists. Then we know if for x near a, Now, mean value theorem tells us fx minus fa equals f derivative at some number c, x minus a, for some c, for some c in a to x. Now, because a and x, they are close. So c, e, x, the three numbers are close. So actually we know f derivative at c by continuity of the first derivative is around f derivative at e. Okay, so we have fx can be represented by fx minus fa. This actually is approximation f derivative at e, x minus e. Then we get linear approximation fx equal represented by fa plus f derivative at e, x minus e. Now here, we only use the first derivative in this approximation. You may ask, can we get a better approximation if we use more, more information, like a second derivative and a third derivative, etc. The thing is, yes, we will have better approximation. Here we use another mean value theorem, the Cauchy mean value theorem. Actually, when we derive L'Hopital rule, we talk about the Cauchy mean value theorem already. Cauchy mean value theorem. Cauchy mean value theorem is a generalization of a Lagrange mean value theorem. So it says this: if we have two functions, capital F and G, and Gx, two functions that satisfy continuous. They are continuous opening or closing of A to B. Two, differentiable opening of A to B. And third, G prime X is non-zero for all X in A to B. Then the conclusion is, then there exists a number C in A to B such that capital FB minus capital FA over capital G minus capital GA equal to capital F derivative at C over G derivative at C, where C lies in between A and B. Okay. Now, if we take a special value, GX applications, so this is the Cauchy mean value theorem. If we take a special value, now, right now we skip the proof right now, and then we see some application example. Now, if take GX to be X, is a special function GX. Then G prime is non-zero. G prime is 1. It's never 0 for all X. Okay. Of course, GX is differentiable and continuous. Then Fx just capital F just capital F. Then you see, then we get a capital F minus capital A minus capital FB over GB. GB is just B. B minus A equal to F derivative at C. G prime is 1. Okay. So this you get FB minus FA equal to capital F derivative at C, B minus A, which is exactly Lagrange mean value theorem, which is a Lagrange, gives the Lagrange mean value theorem. The conclusion of Lagrange mean value theorem. Lagrange mean value theorem. Okay. So Lagrange mean value theorem is actually a special case of Cauchy mean value theorem. Okay. Okay. Now we give a proof of Cauchy mean value theorem. Proof of Cauchy mean value theorem. Proof of Cauchy mean value theorem. Mean value theorem. What do we prove for this kind of mean value theorem? To prove this kind of a thing, what we do is we try to use algebra and then try to rearrange it. So here you see, so these two fractions are equal. So we can use cross multiplication. So what we do is we cross multiply. So FB minus FA cross multiply G derivative at C equal to GB minus GA capital F derivative at C. Okay. So if you write to what you construct is a function. You see here, the derivative is just have degree 1. First derivative. So what do we construct the function is let for instance let capital H X be FB minus FA times GX minus GB minus GA fx. Okay. So the derivative for next check is X is continuous on A to B. Okay, it's very easy. You know, it's a linear combination of gx and capital F. Gf and capital F, they are continuous, and their linear combination is also again continuous. Now, Hx is differentiable. Of course, it's differentiable. Now, differentiable functions, their linear combination is again differentiable. Differentiable on opening of A to B. And then check 3. Is A equal to HB? Is A equal to HB? Plug in A and B. You check this, okay? It's very easy to check. Let's just check the algebra. Check the algebra. So by rule theorem, we actually know there exists a number C. There exists a number C. In this opening of A to B such that derivative C of capital H, derivative capital H C vanishes by rule theorem. I.e., now if you differentiate H prime, then you get a FB, FA minus FA, G derivative, so G derivative X minus GB minus GA, F derivative X, vanishes, at X equals C. Now you plug in C, you get, you know, FB minus FA, G derivative C, 1 minus GB minus GA, capital F derivative C vanishes. Now if you rearrange, we know G prime is non-zero, you can divide. G prime is non-zero by our assumption, it's non-zero. So you can divide, so you get, rearrange this, you get a G derivative, you know, capital F derivative. This is actually equal to GB, capital F okay. Of course, GB minus GA is again non-zero. The reason is if GB minus GA is non-zero, okay, non-zero. If it were zero, then actually you can, by rule theorem, you can actually get a G derivative vanishes, okay, by rule theorem at some number C in A to B. And then this is contradiction. We assume G derivatives never vanishes, okay? So GB is not equal to GA. So actually we don't have zero denominator problem, okay? So we can divide. So this actually done. This proves a Cauchy mean value theorem, okay? And then done, okay? This gives us Cauchy mean value theorem. Okay. So GB minus GA is non-zero. Otherwise, there exists C in A to B such that G derivative at C vanishes by rule theorem. However, we know this is impossible. Impossible. We know G derivative never vanishes. Okay. Now, an application of Cauchy mean value theorem is we actually derived L'Hopital's rule. Okay, we derived L'Hopital's rule. Remember, L'Hopital's rule. L'Hopital's rule. L'Hopital's rule. You know, as B opposite A, then C also opposite A by squeeze theorem. Squeeze theorem. Then you see FB minus FA, GB minus GA. So if we have, for instance, if we assume FA is 0, if FA equal to GA is 0, then you see limit B opposite A, FB minus FA, GB minus GA. Now this GA, GB, FA, GA is 0. So this is actually limit B opposite A, FB over GB. So this is 0 over 0 if you plug in B by A, okay? 0 over 0, you see, this is actually limit. The right side is F derivative C over G derivative C. Here, B opposite A tells us that C are also opposite A, okay? So if you write in another, if you write B and C in terms of X, then you get X opposite A, Fx over Gx is equal to limit X opposite A, F derivative X over G derivative X. Okay, so this is actually L'Hopital rule. L'Hopital rule. From Cauchy-Mield's theorem, actually we can derive L'Hopital rule. So this is 0 over 0. Okay, L'Hopital rule. Okay, so this is an application of Cauchy-Mield's theorem. Now we actually get now talk about the Taylor expansion. Taylor expansion. Taylor expansion. Taylor expansion. Okay. Now Taylor expansion is, you can view Taylor expansion as a more general version of a linear approximation. So it's the following. Let Fx be a function that is continuous, which is continuous, on closing of A to B. And n plus 1 time differentiable. Then actually we have for all x in A to B, all x in A to B, Fx equal to Fx Fa plus F derivative at A x minus A plus F second derivative at A over 2 factorial x minus A squared, etc., etc. Plus the general term F n's derivative at A over n factorial x minus A to the power n, and then plus an error term. Okay, where this error term Rnx is an error term, that satisfies Rnx equal to Fn's derivative, n plus 1 derivative some number C over n plus 1 factorial x minus A to the power n plus 1. Okay, now for some C in A to B. Okay, now the idea of this of a Taylor expansion actually it generalized mean value, it generalized linear approximation. In linear approximation, we don't have a control of the error term, okay? And here we have a good control of the error term, okay? We have good control of error term. Okay, now let's give a proof of a Taylor expansion. This is very important. Proof of Taylor expansion. Okay, proof of Taylor expansion. Okay, first, let's give give that explanation why we should get this form, why we should get this form, why we get this Taylor expansion. Why should get it with Taylor expansion from L'Hopital rule? You know, linear approximation tells us that fx is really close to fa plus f derivative at a x minus a. Okay, so this linear approximation. Now you see linear approximation for x near a, for x near a. Now we want to find how good the linear approximation is. How good linear approximation is. Then actually we compare the difference fx minus fa plus f derivative at a x minus a. Okay, so this is the difference of our function f and its linear approximation. Then linear approximation, we already get the degree 1 term x minus a. So we get actually x minus 2, xa to the term, to the power 2. Okay, to the power 2. And find this limit, x over a. This turns out to be 0 over 0, 0 over 0. Then actually you can apply L'Hopital's rule. Okay, if you apply L'Hopital's rule, then you get differentiate. Then what you get is take a derivative. Okay, take a derivative. F derivative get fx. Now fa derivative vanishes. Okay, and then the degree 1 term. Then you get actually the degree 1 term. You get its coefficient f derivative a. This you get a numerator. We get twice x minus a. Limit x plus a. Then you see. This is again 0 over 0, 0 over 0. If you plug in x by a, you get a 0 over 0. So again, you can apply L'Hopital's rule again. Then you get x over a, 2 times x derivative, you get a 1. And this you get a 2 times derivative of x. Okay, minus f second derivative a is constant. Okay, we take the derivative with respect to x. Okay, so this x opposite a, then use a continuity, f second derivative a over 2 times 1 gives you 2 factorial. So we apply continuity, use continuity. We use the continuity of second derivative of x at a. So you see the ratio is actually a constant. So we can conclude that. Fx minus the linear approximation is around f second derivative a over 2 factorial multiply x minus 2 squared. If you move terms, you see, then you get fx is around, you move the linear approximation to the other side, move the linear approximation terms to the other side, then you get fa plus f second derivative, f derivative a multiply x minus a plus f second derivative a over 2 factorial, or x minus a squared. Okay, you see, this is actually the right side is exactly the Taylor expansion. Okay, the Taylor expansion in degree 2, order 2. Okay, so this way, when we apply more general version of linear approximation, or use L'Hopital's rule, we get exactly the form of Taylor's expansion. Okay, Taylor expansion. The drawback of this approach is we don't have a control. We don't have a control of the error term. Okay, we don't have the control of the error term. If you do degree 3, you know, x minus a to the power 3, this approximation, then you get, you know, fx is around fx fa plus first derivative at x, first derivative at a multiply x minus a plus f second derivative at a over 2 factorial x minus a squared. Now if you write one more, you know, f third derivative at a over 3 factorial x minus a cube, etc., etc. Now, so this gives the Taylor expansion. the form of Taylor expansion. Taylor expansion, i.e. Taylor expansion without error terms. Without error terms. Without error terms. Okay. However, in computation, we want to have a good control of the error term. Okay. We know the error term is small, can be small, but how small it can be. Okay. So we should get a control of the error term. Okay. So now we actually try to use Mean-value theorem or Cauchy Mean-value theorem to get a control of the error term. Okay, try to get a control of the error term. Okay, so here we know fx is n plus 1 differentiable. N plus 1 times differentiable. So if we take now, if you do approximation again and again, so finally you use Taylor expansion. The right side you will be this f a plus f derivative a x minus a plus etc. plus f nth derivative at a multiply x to the x minus a to the power n over n factorial. Okay, so this is the right side is called nth Taylor polynomial. Okay, nth Taylor polynomial. So this is the letter tx be tnx be this thing. So let tnx be the thing. So nth Taylor polynomial of fx. We call it the nth polynomial, Taylor polynomial of f at a. Now, so we know this right side Taylor polynomial is a more general version of the linear approximation to the function f. So we need to find the difference. Fx minus tnx. Fx minus tnx. Okay, tnx. Now we want to find how big it is. Find how big it is. Now we compare it with this x minus a to the power n plus 1. To the power n plus 1. Now actually you can use now for instance we use Cauchy Mean-value theorem. Remember what Cauchy Mean-value theorem says is f of b minus fa over gb minus ga is f derivative c over g derivative c. Okay. Okay. Yeah, actually, we will try to use this. First of all, we know TNA. What is TNA? TNA. Plugging x by a. What happens? TNA? What happens if we plug in x by a is a minus a. You have a bounce a minus a. You get a bounce of zeros. So you actually TNA equal to FA. Okay. Okay. Now if we let so if we let fx capital F, let capital F be little f minus tnx. You see, capital F at a will be little f a minus tna. This will be 0. Okay. Fx, then we apply gx. If we take gx to be x minus a to the power n plus 1. Then ga will be applying x by a. You got a minus a to the power n plus 1. This will be 0. Okay. So the left side, okay. So fx and tnx over x minus a to the power n plus 1. This is actually this is a f x minus fa over gx minus ea. Okay, so we can apply, you see, the right side is exactly Cauchy-Minimality theorem, okay? You check G, this f and g, check that f and g satisfies Cauchy-Minimality theorem. Then we use Cauchy-Minimality theorem. Cauchy-Minimality theorem. Mean-value theorem. If we apply Cauchy-Minimality theorem, then we get a capital F derivative at C over G derivative at C. Okay, C lies in A to B, C lies in A to X, C lies in A to X. Okay, so you check what do you get? Now, first of all, you check f derivative at A also vanishes. You check. All right. So remember, g derivative gx is x minus a to the power n plus 1. G derivative x will be n plus 1 power x minus a to the power n. Okay. So g derivative at a again vanishes. G derivative at a again vanishes. Okay. Now capital F is little f minus Taylor. Is Taylor. Then this is the fx minus f a plus f derivative a x minus a, etc., plus fn's derivative at a x minus a to the power n over n factorial. Now you check capital F derivative will be f derivative minus then all the other vanishes, f derivative plus f second derivative over 2 factorial times 2x minus a, etc. Now if you plug in f derivative at a again, the terms has x minus a vanishes. Okay, then what do you finally have? Actually f derivative at a minus f derivative at a. Then the other is 0, so yeah, I get a 0. So let's return to g f derivative. So this f derivative at c minus f derivative at a, because we just add some zeros. Okay, we add some zeros because f derivative at a and g derivative at a, they are both zeros. Okay, now we can apply mean-value theorem again. Mean-value theorem again. Now this actually f second derivative, take derivative again. So here Cauchy mean-value theorem to f derivative and g derivative. Okay, so this is actually let's use c1. C1 is in A2 C1. And then we get f second derivative C2 over g second derivative C2. Okay, now this way you can go on and on. You can go on and on. You can play this game on and on. Here, when do you actually the end of the story? When is the end of the story? So you see g is n plus 1 polynomial. Is a polynomial n plus 1. So you see g n plus 1 derivative. Then you get n plus 1 factorial. N plus 1 factorial. Okay. Then if you take a higher derivative again, then it vanishes. It vanishes. So this is what we don't want. Okay. We don't want g derivative vanishes. So if you take n plus 1 derivative, then this is actually the end of the story. This is end of the story. So etc. etc. This finally what you get is capital F to the n plus 1 derivative. At c n plus 1 over g n plus 1 derivative at c n plus 1. Now g n derivative is n plus 1 derivative is n plus 1 factorial f n's derivative capital F n plus 1 derivative. You know, this is a, remember, capital F is little f minus tnx to the power n plus 1 derivative. Now Tn, if you look at the formula for Tn is a polynomial of degree at most n plus 1, at most n, degree less than n. Now if you take a degree n polynomial, take an n plus 1 derivative, and then by power rule. So this tells us if you take Tn n plus 1 derivative, one is this. N plus 1 time differentiation derivative of a polynomial of degree less than or equal to n, one is this. So Tn is to the power, its derivative to the power n plus 1, to the n plus 1 time derivative one is this. So this is actually fn plus 1 derivative x minus 0. So this is actually fn plus 1 derivative at x. Okay, so if we play the game of Cauchy-Miemann theorem many times, then finally we get n plus 1 to the power, c n plus 1. Then we are done. Here Cn is of course rising between a to x. Okay, rising between a to x. Okay, so if you finally unravel the definition, finally if you check the Cauchy-Miemann theorem, what do we get? The equation, then what do you get is fx minus tnx over x plus a to the power n plus 1 equal to fn plus 1 derivative at some number cn plus 1 over n plus 1 factorial. So if you move terms around, then what you get is fx equal to tnx, the Taylor polynomial, plus the error term, plus the fn plus 1 derivative at some number cn plus 1 over n plus 1 factorial, multiply x minus a to the power n minus 1. Okay, so this is this thing is called error term, Rnx, error term. Okay, error term. Okay, so if x is really close to a, then x minus a is really small. Okay, x minus a is really small. Okay, and also n plus 1 factorial is also big. Denominator is big. Okay, so we get the Taylor expansion. Okay, so we got a Taylor expansion. So you see, Taylor expansion gives us an approximation of the function f plus some error term. Okay, some error term. Okay. Okay, corollary. Now you see, this is approximation. Now you may ask, okay, if n approaches infinity, can we get a better and a better approximation? And this approximation not just approximation anymore, it turns out to be equal. Okay, so in which situation can actually we get an equation? This is the following corollary. If we have good control of the error term, i.e. the error term approaches 0, then actually we see the function converges to its Taylor polynomial. Okay, corollary. Okay, if Rnx approaches 0 as n approaches infinity, now of course we assume as that f is infinitely differentiable. Then actually we know then limit fx equal to limit tnx n approaches infinity, i.e. we get an approximation of the function f by its Taylor polynomial. Okay, Taylor polynomial. So the corollary is corollary. If we have good control, okay, so suppose that f is infinitely differentiable, so we can push this n to infinity. So if f is infinitely differentiable, infinitely differentiable, if fx is infinitely differentiable, so that we can take the limit n approaches infinity, infinitely differentiable on a to b. Okay, i.e. we can take nth derivative for all n, and the nth derivative of x is bounded for L, bounded by L for all n all x, for all x in a to b, and all n. So it's uniformly bounded. Okay, all the n and all the x value, they are bounded by L. Here, this x value is in finite interval. Okay, bounded all n. Then now you see, then actually the limit, then Rn. Then actually Rn, you can check Rn approaching 0. Okay, Rn approaches 0. Rn. Then Rn approaches 0. Rn, which is fn plus 1 derivative at some number c over n plus 1 factorial x minus e to the power n plus 1 approaches 0. It's very easy to check. Okay, it's very easy to check. This thing approaches 0. Then we have fx equal to fa plus f derivative at a x minus e plus f second derivative at a over 2 factorial x minus e squared, etc., etc. Now the general term is nth derivative at a over n factorial x minus e to the power n, etc., etc. So this, the right side is called Taylor series. The right side is called Taylor series. Taylor series. We call the right side. The right side is called the Taylor series. Taylor series for the function f, for fx. The Taylor series for the function f. Okay. Another thing is if a is 0, if a equal to 0, if we take a to be 0, then we get the Maclaurin series. Then we obtain the Maclaurin series. Maclaurin series for f. Okay, i.e. the Maclaurin series of f is simply Taylor series at 0. Okay. Example. Okay, example. Fx is e to the x. Okay. Okay, so here we take x to be bounded. X is bounded. X in a to b, you know, bounded. Then f derivative is e to the x. Okay, you know it's invariant. F derivative is invariant. So nth derivative of x is again e to the x. Now e to the x is bounded. Okay, bounded. So which is bounded? The derivative is bounded. So all derivative, all nth derivative, derivatives of f is bounded for x in some finite interval. So derivative is bounded. Then actually we can every nth time derivative is bounded uniformly. Excuse me. So actually we know by the above corollary is by the above corollary, then actually we know the Taylor series equal to the function f. Okay, then the Taylor series explains. Then we get let's see, it's Maclaurin series. Okay, f nth derivative at 0 is e to the 0, which is a 1, which is 1. So fx equal to its Maclaurin series. So we get fx equal to its Maclaurin series. Maclaurin series f0 playing f derivative at 0 times x minus 0 plus f second derivative at 0 over 2 factorial x minus 0 squared, etc., etc. Now derivative, nth derivative is just 1. f0 is also f0 is e to 0, which is 1. So this is 1 plus 1 times x minus 0 is x. X minus 0 squared is x squared. Now f derivative is, if you write more terms, 3 factorial x to the power 3, okay? So you got a 1 plus x cubed, x squared over 2 factorial, plus x cubed over 3 factorial, plus etc., 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 okay? So the right side is Maclaurin series. Maclaurin series. Maclaurin series for e to the x. Okay, actually the right side of Maclaurin series converges for all x. Okay, it converges. You can determine the radius of convergence. It turns out to be infinity. So we get actually e to the x equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc., etc. Okay, so this actually n from 0 to infinity x n power n over n factorial. By definition, 0 factorial is defined as 1. Okay. 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 So now you see we can actually do something. Okay, then for instance, if we plug in, take x to be 1, then we get e is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, etc., etc. Now remember the value of e. E is around. Now if you use Sage, if you ask Sage what e is, we actually know e is around 2.718. Okay, if you use Sage, then okay, you can write any terms to it, etc., etc. Use Sage. Now you see the first two terms, 1 plus 1. The first two terms gives 1 plus 1 gives us 2. Okay. Now the first two terms gives us 2. First two terms. So we get 1 plus 1, which is 2. Now first three terms. 3 terms. 1 plus 1 plus 1 over 2 factorial. This is 2 plus 1 half. It's 2.5. Now four terms. Then you get 2.5. 3 terms plus 1 over 3 factorial. This is 2.5 plus 1 over 6. This is 2.5 plus 0.16666. So you get actually 2.6666. Okay. Now if you add another term, like a 4 factorial plus 4 factorial, 4 factorial is 1 over 24. Okay, it's around 0.04. Now you see 2.666, etc., etc., plus 0.04. This is actually 2 around 7, 0.6, etc., etc. So it's close now. You see, you can get object close to the number e. Okay, you can get an object close to the number e. Okay. Okay. Now, so we have the Taylor-Maclaurin series for E, which is 1 plus x squared over 2 factorial plus x cubed or 3. Excuse me, etc., etc. So it's nth power O n factor n from 0 to infinity. Okay, now we know exponential functions. Sorry, exponential functions ex plus y. They satisfies e to the x plus e to the y. Now, how do we check the right side also satisfies this property? Okay, check that. Okay, wait a second. My battery is low. Let me get a charger.